Good afternoon. My name is Azibayam, and I'm a postgraduate researcher here at the James Watt School of Engineering, University of Glasgow. And today I want to give a talk on reactive transport in carbon dioxide geological storage. I'm a member of the GeoEnergy research group, and our research here at the group focuses squarely on understanding how fluids such as CO2 and hydrogen flow through complex materials and how these processes affect sustainable geoenergy systems. Our group is led by Dr. Hiwa Zhang. Before delving into my research in particular, I'd like to give a general overview of what CO2 storage essentially entails. CO2 storage, or CO2 geosequestration, describes a mechanism through which we aim to manage carbon emissions. It essentially describes the capture of CO2 and its eventual storage. So the way it works is by capturing CO2 from CO2 sources such as power plants. We inject that CO2 underground into rock formations, and hopefully those rock formations would act as natural storage containers to keep the CO2 for a very long time. In the UK, the hope is to eventually achieve carbon emissions by 2050. Separate countries have different targets. Generally, when the CO2 is injected into the reservoir, it's trapped following different mechanisms, one of which is the structural trapping, where the CO2 is trapped under a tight cap rock. The cap rock essentially acts as a seal which stops the CO2 from flowing upward. You can think of it like a cap or closing a full water bottle. Another form of trapping is residual trapping, where the CO2 is broken down into tiny bubbles and trapped within rock pores as water flows back after CO2 injection. Another form is solubility trapping, where CO2 dissolves into the ubiquitous brine that are present in the rock formation, and once it dissolves, it can't escape. Finally, we have mineral trapping, which describes the situation where the rock interacts with the CO2 to form more stable carbonates. It's the slowest form, but it's essentially assures permanent trapping of the CO2. So my research is on reactive transport, which describes the interaction between the CO2, the brine, and the rock formation. Generally speaking, reactive transport essentially describes the interaction between fluid flow, chemical reactions, and transport within the geological media. It's a very important process. It occurs naturally within Earth systems. But in CO2, it's especially important because reactive transport can affect the rock itself. It can affect the behavior of the rock. You can change the rock, the pore structure of the rock, its flow paths, and how well it can trap CO2. So to understand this in detail, we carried out an experiment using advanced X-ray imaging. So we did this experiment at the diamond light source, where we essentially injected CO2 into a natural reservoir, a natural rock, and using X-ray images, we can observe how the CO2 behaves within the rock, and we can see this process over time. These images, you can see, they show the pore structure of the rock as it evolves over time. Initially, the pores are small and disconnected, but as CO2 reacts with the rock, minerals dissolve and the pores begin to grow and connect. This obviously changes how the fluids flow through the rock, and in some cases you can expect that this can affect the potential for CO2 storage within the rock system. This is a 3D render that shows how these small changes accumulate over time. As you can see, the pores were effectively disconnected, And you can see how, as the solution occurs, the pore structure, or the pores, became more connected and enlarged over time. And as you can expect, this would most likely lead to increased transmissivity of fluid within the rock itself. So to quantify this, we can see using these graphs, the porosity tells us how much empty space the rock has, while permeability tells us how easily fluids can flow through it. As reaction progressed, you can see from the graph, porosity increased, and so did the permeability. This essentially means that the rock became more likely to allow fluids to flow within it. But the most important question for us was to basically explore how that changes in porosity and permeability, how the evolution of the pore structure can affect the trapping of CO2 long term. And we conducted what we call the drainage and imbibition experiment. But the drainage experiment describes a condition where CO2 is being injected into the reservoir. And before the reactive transport, you can see what you typically expect in most reservoirs. After injection, you see a good injection of the CO2 within a good amount, most of the pores. But after the reaction, due to the evolution of the pore structure, CO2 preferred to flow through the more enlarged pores. You can see this as well. Then we conducted an imbibition experiment, which is basically to flow water back into the reservoir and effectively trap the CO2 in a process called residual trapping, as described earlier in previous slides. Before the reactive transport, you can see that there's an effective amount of CO2 being trapped after imbibition, but after reactive transport, due to the enlargement of the pore spaces, it was quite easy for brine to flow through the rock and displace the CO2 that was originally trapped. So basically what this tells us is that the microstructural changes that occurred as a result of the reactive transport significantly altered the pore structure. And these changes also reduced the rock's ability to trap CO2. And this basically happened through the occurrence of large connected flow channels. So what this tells us is that reactive transport potentially could have a negative effect on the long-term storage of CO2 in a reservoir. Further investigations in this experiment, we did this in isolation. We would like to see how the CO2 would occur when we inject how the reaction would occur, when we inject both CO2 and the brine together into the rock systems. This way we can see how the two rocks will interact and how these can affect the porosity and permeability, and we can see how they compete for pore space within the rock. Thank you very much.